Okay, we are starting on chapter 13, which is on simple linear regression. So our goal here is to describe a linear relationship between two numeric variables. So we're not dealing with categorical variables. We're strictly dealing with numeric variables, or generally it's going to be continuous variables, but they can be discrete as well. But the goal here is to describe this linear relationship between two numeric variables. So our first variable, let's call it the explanatory variable, or we could say the predictor variable. It's used to make a prediction. So we want to make a prediction or explain some outcome. Whereas the second variable, is the dependent variable, or the predicted variable, or the response variable. We can use any of these names interchangeably. And it's the variable of interest to predict or explain. So what we want to do, let's call this dependent variable y, and this explanatory variable x. So the goal is, can we explain or predict values of y from x, right? Can we predict values of y from x? That is essentially what we are trying to do with linear regression. So we're asking ourselves, is there a linear relationship between the explanatory variable and the dependent variable? Can the explanatory variable predict or explain values of the dependent variable? So basically restating what we have, but basically, can x predict y? So let's actually go back. This is chapter 3, I believe. We discussed the idea of correlation, which we just called R. And it's the covariance between x and y divided by the product of their individual standard deviations. So the standard deviation times the standard deviation of y. And we said that correlation measures the strength, both the strength and the direction of the linear relationship between two numeric variables, and we can call them x and y. So correlation is a great starting point for this. So correlation is not really trying to determine if x can predict y. That's what we're trying to do now with linear regression. Instead, it's just seeing, do they move together? If x increases, does y increase or decrease? If y increases, does x increase or decrease? So it'll tell us the strength. Recall that correlation is between -1 and 1. So strength, we mean the correlation is stronger when we are closer to values of -1 and 1. Right? A one-to-one relationship means that if x increases by 1, y increases by 1. Whereas a correlation of 0 means there's no relationship between the two variables. So the direction, if it's negative, they move in opposite directions. And if it's positive, they move in the same direction. So if you need to brush up on that recall that this is from chapter 3, correlation. So let's actually go back to an example. So if you were in my Stat 1 course, we discussed the relationship between horsepower and gas mileage of vehicles, cars. So we created this scatter plot, and you can see we have horsepower on the x-axis, and we have miles per gallon on the y-axis. We can see that as x increases, y decreases. Right? We're moving, we can see generally in this direction. It's a negative relationship. They seem to be moving in opposite directions. And we actually calculated our correlation here, and our correlation was equal to negative 0.78. So that's a pretty strong correlation. It's pretty close to -1, and it's obviously negative, so they move in opposite directions. So when one increases, the other one decreases, and vice versa. But now, our question is, can horsepower actually predict a car's gas mileage? Okay, so they obviously move in tandem. When one increases, the other decreases. But what predictive power does horsepower actually have on gas mileage? And the question the way we're going to answer that question is to use linear regression. So the goal here will be to create a line of best fit. So we might think a line of best fit would look perhaps something like this. Right? That would maybe make sense compared to a line that was, say, looked something like this. Right? This line is positive. This blue line is positive, but we know that correlation is negative. So this blue line really doesn't make any sense. So we should know that this line of best fit should be negative. So we can see that this does have a negative slope. But then the question is, okay, well, which line is best? Is it this line? Or how about this line? Right? We can technically draw an infinite number of lines, but the question is, how do we get the best line from into the scatter plot? So the way we're going to answer that question, how do we fit, or how do we create this line of best fit, or what we're going to end up calling it, the regression line? And the answer is simple linear regression. And this is the topic for this chapter, chapter 13. So we're going to explore this concept throughout the rest of this chapter.